Hello everyone, welcome to the CSE116 Task 4 overview. It's been a long ride so far, and I'm glad that you guys have made it here because, as we know, Task 3 was a little bit lighter than Task 2 and probably Task 1 as well. So you could probably expect the same for Task 4. Definitely shouldn't be that much harder. In fact, I think you guys are going to love this task. So let's actually get into some things we're going to need to know for this task. So binary trees, we love them. Um, yeah, so we're gonna go over some stuff about binary trees. Also, some of you may remember from test two, there is a certain way to traverse these trees that I really love, and actually, it's like the necessary way basically to do it, or else you're going to run into a lot of trouble trying to do it the other way. So we're gonna talk about that a bit, why we're even using them, and decisions. What I mean by decisions. Okay, let's talk about that a little bit. So we're gonna take a step back and think about inheritance. So you guys learned about inheritance. We dealt with all that in test three, and it's coming back because it's very useful, and we're using it for this task as well. So I'm going to define to you a decision because in this task we're going to implement something called a decision tree, and we are going to advance the enemy's AI, and technically we have this system that we could expand many other behaviors of other things, um, but in this task specifically we encourage to use this for an enemy. But anyways, we're going to take a step back and just talk about what is a decision. So a decision has the following behavior: a decide method that returns a boolean, and a do action method that returns a void. So decide is just some condition that will direct the traversal of our tree, as my bullet point says here. Meaning that when we eventually go through our tree in the future, this decide method will help us choose like down which branch to go, either right or left. And do action is logic that we should execute after we've already made our way down the tree, and we are at a leaf node. And I'll define what a leaf node is later. Also, a decision has some simple stuff. It's going to have some instance variable, maybe string for its name, and we have some basic getters and setters. But the things that we really care about for decisions are its decide method and its do action method. And what I'm going to describe is that only one of those really matters at a time. So we're going to take a look at this example here. We have a low HP and near player decision that extends decision. Okay, so low HP is a decision. It extends it. So it naturally has the ability to override its methods, such as decide or do action, right? So here I present two decisions because these two classes here are children of decision. And for example, we're going to take a look at low HP. I override the decide method in low HP, and I say that decide will return true if whatever behavior we're on, say like a dynamic object, is at low HP. Which, we might pass in some parameters to actually compute that. But what I'm just trying to convey to you guys is that we could override this decide behavior in our child classes that extend a decision. Our decision is going to be our upmost parent class, our superclass, and we're going to make a bunch of decisions from that template. Um, and I also have an example near player that is also a decision. It extends decision, and its decide method returns true as long as its dynamic object, whatever it is near a player. So with this example, I present to you two different subclasses of decision that have different behaviors for the decide method, which is cool. But you might be wondering, what about do action? Well, in these scenarios, I didn't override do action, and that's actually because um, any subclass that extends decision should really only override either the decide method or the do action method, and that is because of the behavior of our tree. Only the leaf nodes can execute a do action call. So it's kind of not useful to have a definition for do action for any nodes that are not leaves. And we'll get to what that exactly means in a little bit, but just keep that in the back of your mind right now. I'm going to move my head up here because I noticed I was blocking a bit of the other thing, but that thing I was blocking up here that just said returns true if near player. Anyways, so on this slide, I present more scenarios of extending the decision class. But you might notice, oh, we have our previous ones, low HP and near player. These are two like states that I also have here, but I'm also showing that we could have decisions that only override the do action method. So, for example, here we have heal, and heal overrides do action and simply heals the dynamic object whatever it's given when called. Again, this logic is something you guys are going to implement, but right now we're just talking about the behavior of our decision tree. And we're not at the tree yet, but we have to define what a decision is to be able to make the tree. So we're saying heal will be a leaf node because it's supposed to execute behavior, and we have a definition for do action, meaning that we intend for this to be like somewhere at the bottom of our tree. Um, and it heals just when do action is called. And we have another one here, move towards player, that if you call do action, it will slowly move the object towards the player. Okay, simple as that. Displayed here, again, I have 4 subclasses of decision. They all extend decision. Again, up here we define that a decision has like a get name, set name, meaning that all of these subclasses will have extended that behavior from decision. These are all children of decision, okay? So if you weren't feeling very confident on inheritance, hopefully that we're clearing some stuff up now because this task definitely requires some good understanding of it. Now, with all of this information, we can make a binary decision tree. So, you guys have started learning about binary trees and stuff in class, and so here I will start our tree. So we have our root node, and I'm declaring it to start at low HP. Okay, you guys can design your own decision trees, and you're gonna like probably read about some of that during the task handout. But right now we're just talking about this specific example. So I put low HP. This is a binary tree node at the root of our tree, and every binary tree node has a left and a right. Now the left and right of this node is null. So technically, this node is a leaf because I will define leaf now. A leaf is any node in the tree that has a null left and right. So technically this is a leaf because it's the root and its left and right are null, but this isn't a really useful decision tree, especially because low HP overrides decide. And because of that, we're not able to do any do actions. So this is kind of a useless tree. But we are going to build it, and this is just our root node. So let's move on. Oh yeah, so if the decision is true in our decision tree, you're going to travel to the right in the tree. Otherwise, if the decision is false, we travel left. And yeah, here I define leaf. And yeah, we only execute do action on leaves. So if you're confused about this decision part right here, I'll briefly describe that again. So this is our root node again, low HP. It is a decision. It's low HP extended decision, but it is a decision because, that's our parent class. So um, it overrides the decide method. If this method returns true, that is telling our tree that once we start at the root, we want to go right. If this is false, then we'll go left. Okay, and right now we don't have much to traverse right now, so it's not really a useful tree. Again, let's look at more examples. So we expand our tree. Now we have a left and a right node to our root node. That is not null. So so I didn't define targeting player before. I believe I had a few different examples here. But I'm going to present another decision because it extends the decision class. Targeting player is a decision, and here I'm going to override the decide method again. And for the targeting player, I'm just saying that it returns true if the end node of the path is near the player. Again, don't worry too much about what I'm saying there. This is just for the example. We go more explicitly into that in the doc. But so we're slowly building our tree, and now we have two leaf nodes, and our root node is no longer a leaf because its left and right are not both null. So we have two leaf nodes, and we are evolving our tree. Now let's say I had we started at the root and low HP, the decide method returned true. So we'd go right. And now, since we have another decision, this is a leaf. So we technically stop here and we would execute do action because this is a leaf. However, this doesn't override that because we're still building our tree. This near player does not have a do action definition, but let me advance one more slide and we'll look at some things that do have do action behavior. Okay, so this is what I'm going to present as our complete binary decision tree. We have low HP, targeting player, and near player. All of these decisions override the decide method. Okay, and all of these decisions on the bottom, recalculate path, move towards player, heal, and run away, they all override do action. Now, that means that these up here, remember, any node that is not a leaf is expected to have the decide method overridden. So there's some behavior that directs us on which direction to travel in the tree. Now, we're going to go through some examples of actually traversing this tree, but I'll just briefly go through back some definitions. Each one of these nodes on the bottom is a leaf. They all contain different definitions for do action. Now here again, I added two new ones. I added recalculate path and run away. And you guys might intuitively, if you just look at this tree right now, you could like see some decision making we can make, right? So before we go into actual logic, we'll say, okay, if I'm low HP and I'm not targeting the player, then I want to recalculate my path. Makes sense. If I am low HP and I am near the player, then I want to run away from the player. That makes sense for an enemy to do, right? And we can see the kind of flow of logic here where until we get to the bottom of the tree, we're like picking somewhere else to go, right? Like these things aren't doing behavior. We're just asking them like, hey, like which way should I go? And we're going to look at a specific example now. Okay, so here I'm going to define an enemy, and this enemy is going to possess this decision tree, okay? And I'm going to define some state of the enemy. I'm going to say its HP is 3 out of 10, and its distance from the player is 10, okay? So, with that information, let's traverse this tree. So, we're going to start at low HP, our root, okay? And we're going to try to pick where to go next. Now, low HP is going to have to like be defined explicitly, like what determines if we're low HP. But I'm just going to tell you right now, I'm going to determine if something's low HP as long as it's under 5. Okay, so let's look at our HP then. Are we low HP? Well, 3 is below 5, so I'm going to say yes. Now, low HP, this decision here, the decide method should return to us then true. And if the decide returns true, that tells us we need to go right in our tree. So we listen to that. The decide returned us true. We go to the right. Okay, now we're at near player. This is another decision. Is near player a leaf? No, we have nodes like to left and right. So it's not a leaf, meaning that we still have deciding to do. So we ask near player, hey, decide. What should I do? Am I near the player? Well, my distance from the player is 10. So I'm not near the player. And if I'm not near the player, then I'm going to want to heal. And you might start to understand now the kind of intuitive flow of this tree. But, however, we get to a special case now. We get down to heal. And we ask ourselves the question, is heal a leaf node? Well, its left and rights are null, meaning that it is in fact a leaf node. And if it is a leaf node, now we've reached the bottom of our tree. We've made all the decisions that we want to make. And we want to call do action on that leaf. So we traversed through our tree, we reached heal, and now we're going to say, hey, let's heal. So we called heal here, and we increased our health to 6 out of 10, which is exactly what we expect from this tree. We want to make advanced enemy decisions based on the logic we implement here. So we healed, now our HP is 6 out of 10. Great. Well, I'm going to restart now because let's say this is one call to traverse, and we want to be doing this like multiple times a frame or something like that. Like we want the enemy to be making like constant decisions, right? That just makes sense for our game. So now our HP is 6 out of 10. And I previously defined that I'm going to say something's low HP if it's below 5. And now we're at 6, so we are no longer low HP, meaning that the decide method of low HP should return false. And if it returns false, we go to the left. Now we are at targeting player. And I added some more state to enemy because I realized I forgot. But we're gonna say that the end node of the path for the enemy is a meter from the player or whatever units. Okay, doesn't really matter. But that to me says that we are in fact near the player. The end node of our path is near the player, and all of that is also just saying that the decide method of targeting player should return to me true. Okay, again, that's explicit in the doc. But okay, so decide if it returns true. That means I expect to go, think for yourself, the right direction of the tree. Because any true value from decide tells me to go right, any false value would have told me to go left. But since I am near the end node is near the player, I'm on the right track. Well, then move towards player. Execute this, move towards the player a bit, and yeah, I think I have some more examples here. You can see the distance from the player thing keeps getting updated as we're moving towards the player. This tree will constantly be re-updating every single frame. And yeah, that's basically the decision tree. One more thing I wanted to add here was I wanted to show you guys the actual implementation of this game. So I am in the game, and as you can see, these enemies are following me just as before. But if I move around a bit, you can see that they're going to recalculate their path and go better towards me. We can definitely see that with this guy up here because he usually just like get stuck and all that. So if this guy comes down here, I'm going to shoot him, and you can see he's low health. He's running away. If we go over here, oh snap! I took some damage. If I go over here, hit this guy. The legends are a little rough up here. Hit him. He's gonna also run away, and he healed up, and now he's coming back towards me. And yeah, same thing with this guy. He healed, and now he's going to find me again. I'm gonna hit him again. Now he's gonna go heal. I'm gonna run away a little bit, and yeah, now he's going back to find me. So as you can see, just like the decision tree that in the example that I showed, these enemies work exactly that way. It's the same behavior tree that I just showed you. So this is how it's going to look in the game, and you could think how much farther you could go with this. You can make these guys a lot smarter. You could do a lot more cooler stuff. This is just the example that we showed. Also, yeah, you can see the invincibility frame thing that I was talking about, and it takes more than one shot to kill these guys. So yeah. And then one more thing, I think it's important to talk about why a decision tree is not a binary search tree, although it seems very similar. So here I have presented a BST, a binary search tree, and you might notice some similarities from the decision tree we talked about. Let's say like we wanted to get to the element 4, okay? We would go down the left, then to the right, and we get there. Just like, in our decision tree, we might go down left, then right, and then we're there. But it's actually done much differently. So first of all, binary search trees need a comparator because they are in sorted order. Our decision trees are not in sorted order. Um, the specific sorted behavior of a binary search tree is the whole deal of why we basically use it. It's super efficient and we could find things very fast. And that's why we use binary search trees. And every element has to be sorted by some comparator. So I get that there's some parallels in class, like with the side methods determining like these true or false values, similar to a comparator, but decision trees are not comparators. They're not in any sorted order.
we could technically keep going down the right forever in true or false pattern. But we're not really looking for anything. They're not sorted. They just have a similar way of traversing the trees. Um, but yeah, I just want to make sure we point out some differences there. Since we have seen comparators in class and they're similar, but BSTs provide the specific behavior that every node in the tree is sorted by a specific comparator. So, just wanted to add that.
So, hopefully this visual was useful to you guys because this is exactly basically what you're going to implement. But we will get to the doc now and like look at some stuff explicitly. But yeah, I hope that was a good explanation. And if you need to pause and just look at it while you're working on it, feel free to. And yeah, okay. I decided I'm going to keep my head up here for now. It's nice up here, so I'm just going to leave it here for now. But okay, we're in the doc. We're going to brief through it. We're not going to go like super explicit, but we'll take a look at everything that like needs to be done. And yeah, let's just get started right into it. So right off the bat, we're tasked with doing some quality of life things and slightly making our game make more sense. So before we actually like implement AI stuff, we're just going to make a few changes to our game. First of all, we're going to add these things called invincibility frames. And a lot of you probably could already infer what those are. But if you don't know what those are, they're basically just a few frames in the game where after you take damage, you can't get hurt. So it's just like a very short period of time where you just can't get damaged anymore if you got damaged. And that's going to make our game way better. We're not going to instantly die to our enemies anymore. And also, enemies won't instantly die to us. So, yeah, we're going to implement those in dynamic game object. Also, we're going to make a projectile not instantly kill our enemies. And enemies going to I think do some damage to us instead of yeah. So enemies are gonna actually do like some damage. It won't instant kill us, like I just described. And we're also going to be refactoring update and moving it into dynamic game. Actually, no, we're going to be doing something later with our decision trees with update. So when it says delete update, be kind of careful. Comment it out. That's my recommendation. Don't delete it because you're probably gonna want to reuse your code from it, or at least a lot of it. So yeah. Also, we also just say some things here about like you could change projectile damage and all that, and make your game harder, which is fun if you want to do it. So yeah. Okay. Now we get into the stuff that I just described. The decision tree, binary search trees, or sorry, binary trees, and decisions and all that. So yeah, here we describe the decision class, and if you remember all the way over here, the decision, right? This thing here is what is also described in the doc, right here. So we have like get name, set name. We have a decide method that takes in some references to some other objects that we could use in making our decision, and a method called do action. Now remember, decision is going to be our parent class for a whole bunch of children decisions. Um, so yeah, that's great stuff. And then we're going to make the decision tree class. And then we go through a whole bunch of logic here, which I will talk about, of course, because this is what has to do with binary trees, like what I explained in the beginning of the doc. Um, so, like test two, I recommended that you guys do recursion. And that's because recursion is just great and all when working with linked lists, but kind of necessary when working with binary trees. Um, Now, I wouldn't try to do binary trees with while loops. Seriously, recursion is the way to go. I believe sometimes Jesse challenges if you could do it with a while loop, like he'll be impressed because it is seriously just not easy work. It is the better way to do it with recursion. So really try with recursion, which is also why I recommended it in test two to get some practice with it. But anyways, let's talk about some stuff here. So we're going to be making some basic getters and setters. You guys know the deal with that at this point. And we're going to be creating a method called traverse. Now, Traverse is the exact operation that I just presented in the slides. So if we go back here, traverse is doing this thing. Okay? It is going through the tree until it hits a leaf and then returning, I believe, returning that node. Um, yeah, so it returns a reference to the decision. Yeah, we want to return the leaf. Now, if you read this explicitly here, which of course you should, always read the doc. It's going to traverse through the tree in the exact way I showed you. You're going to go to the right if the side method of the decision node is true, and left if false. So and once you reach the leaf, that's what you're going to want to return. And you could already imagine why this might be a tough operation to do with while loops. It just makes more sense to do it with recursion. Trust me, it's worth it. Okay, I might talk about that a little bit more, but I'm going to just get through more things here first. So, we're also going to be making something called reverse, which is going to have to walk through the whole tree and reverse its nodes. Because, for example, reversing a like enemy, for example's binary tree could be like confusing it says this in the doc, but like if on low HP, if I'm close to the player, I'm supposed to actually run that and I heal, then like the enemy would do like not expected behavior. Anyways, if that makes sense to you, it makes sense. If it doesn't, well, you still gotta make it anyways. So yeah, we have to make reverse, which does exactly as this picture shows here. For every single node, we want to swap its left and right. For every single node, we want to swap its left and right. That like basic description can help you set up your whole recursive call. I'll just tell you that right now. And remember in class, like we learned about different types of traversals, in order, whatever, all that stuff. This one doesn't really matter which one you choose. You just want to go through it, the tree, use recursion, and for every single node, swap its left and right. That's reversing the tree. Okay. Um, and then we get into our decision child classes, which, if you remember, or you might recognize, these have very familiar names. So just as I showed in the slides, each of these decisions will either override decision or do action. Never both. As we can see here, move towards player overrides do action. Targeting player overrides decide. We never do both. We only do one, and that's only to help us traverse the tree. And each of these things are like are gonna have different behavior on them. Um, and these are not like they do have some difficulty to implement a little bit, but there's really we try not to make these extremely difficult because you're already making a lot of classes here, so the logic isn't that bad. Especially if you want some advice. This is move towards player is where you're going to want to use your update logic, which is why you shouldn't delete it. You should comment it, bring it back here, because move towards player. Don't overcomplicate it and write it all again. Use your old update logic. It's just that's what you should do. And then all this stuff here, like heal, recalculate path. Some of this is like, like heal might take like a little bit just to understand what to do, but once you understand, it could be not too hard for you. Um, but overall, I understand this is a hefty task. We're looking at trees for the first time, doing a lot of recursion. So please come to office hours. Please look at the visual on those slides to understand what a decision tree is actually doing. Um, it's really cool and it's going to help for our game. But again, I understand it's tough. So if you're having trouble, come to office hours. Okay, moving on. Dynamic game object, we're going to just give it basically some state to have a decision tree. So yeah, you guys can read through this. Not too much to say about that other than making your methods that you guys are used to making by now. But let's talk about testing utilities real quick and requirements. Oh yeah, this is actually very important. So, we're going to talk about first a testing utility that compares two binary trees of decisions. Now, we are basically just asserting that we're giving this method two binary tree nodes. Just so, as you guys know, binary trees are similar to linked lists, right? Traversing them, you have to like loop through or use recursion. But we're gonna have basically two root nodes of these trees, and we're going to go through these trees and we're gonna go through the same exact time and compare the decisions of each of those nodes. So if we're at the roots, we want to compare that the decisions names, that's what we're comparing, of these two nodes are equal. Then we're going to go down maybe like both these nodes here, compare, and then however big the tree gets, we want to make sure that they have not only the same decisions names, but that like if the left node of tree 1 is null, then the left node of tree 2 at the same spot must be null. So yeah, that's that. Um, Now, to test the behavior that is required for testing requirements, like your traverse and reverse methods for the decision tree, um, you guys really should um make a testing decision. Okay? Meaning that just like these over here, like low HP, near player, targeting player, you should make a decision that extends decision, right? Call it like testing decision or something, and override its behavior, um, its decide and maybe do action. Take that as you will, to help you test. I'm telling you right now that doing this will make your test so much easier. I did it when I just did this task. So please do that. I think that like this is such a strong recommendation that they might even update this doc a little bit for that. But and if you're confused on that, we could help you set up in office hours. But really do try to think about it yourself and why it would even be useful to override your own testing decision. Because if you could understand that, then you're well on your way for understanding binary trees and like this whole decision like algorithm. Um, and then we're talking about testing requirements, which are just testing traverse and reverse for the decision tree, which is way easier if you do what I just told you again. Um, but testing these, aren't I'm not gonna say they aren't too bad, but they are simple in the way where, like reverse, for example, most of the work done here is just setting up two trees and then using your testing utility. Traverse is a little more complicated. You got to make sure that you do this whole process correctly, like that you do this the right way. Which if you think about, okay, if I'm testing this behavior that I'm showing you right now, why would making your own node, your own testing decision be helpful? Think about that a little bit. But that's the task in a nutshell. Um, Again, this is not an easy task. I understand that. So don't feel bad if you don't get this right away, but please start early so you can ask questions on Piazza come to office hours. Because yeah, binary trees, linked lists alone maybe were like kind of tough to understand. Like they're just scattered throughout memory, and we have references that point to another. And now binary trees are just like a more advanced version of that now, and we're doing an algorithm on it. This whole decision tree thing, I get it's a lot. So, that's basically that. I don't know if I want to say anything more about like traverse here. Um, just keep in mind that like this is an algorithm and you should use recursion, okay? But you can't blindly do it like just how you saw in class with like one of the traversal methods, because you want to return something once you get to a leaf. Like the second you get to a leaf, you want to return it wherever that leaf is. Remember, like this presentation here, like you're going to traverse the tree, you're going to start your route, go some direction, go some direction, and every time you go to a direction, you're checking if it's the leaf. And then eventually you'll hit a leaf. And once you hit that leaf, you're gonna want to return that. And that's what traverse does. I can't really get into too much exact implementation anywhere here because this task is it is a hefty one, but it really does make sure that you understand the material. If you get this done, you're well on your way to being great at OOP, more data structure stuff. And yeah, I am proud of all of you for making it this far. I know task 2 was not easy. Task 3 was a little lighter, and yeah, task 4 is obviously the easiest one so far. So you guys will probably have a great time doing that, and it's all gonna be fun from here. So yeah, I think that's pretty much all I want to say about this task. Again, any specific questions, please come to office hours earlier because it's going to get packed later on once the deadline comes in for this one. So yeah, ask questions and yeah. So I think that's pretty much it, guys. I hope you enjoyed. If you did, please smash that like button and subscribe, and I will see you all next time.